So I've been meaning to do videos like this for quite some time now. So I thought of starting with this topic, and I've made an attempt with this topic before, actually not so long ago, but the videos that came out weren't that great. So I just thought of redoing this just once to see that to see if I could do better. Hopefully, I do better. Anyways, so the topic going to be going over is immutable radix trees, and I will be going over a very specific implementation of immutable radix trees. So there is one by Hashicorp. It is the library that I'm going to touch upon is written in Golang, and you can see that here. So they've created this iradix package that implements an immutable radix tree. Package only provides a single tree implementation optimized for sparse nodes. So my main focus will be on the fundamental pieces of this code base, or at least some of the important things, right? Maybe not all the fundamental things. For example, I don't think I will be covering iterators and raw iterators and reverse iterators, but I will cover what a node, a tree, a transaction looks like and how all that works, and maybe how something like an insert works or a get works, right? Uh, so, like I said, I'll be going over those things in a future video. In this video, I just want to get an overview, give an overview of certain aspects of the immutable radix tree. And before I want to do that, I briefly want to touch upon a radix tree. I won't be going too deep into theory. If you are really interested in the video, I suggest you have a look at Wikipedia and try to understand what a radix tree is and what are the operations possible in radix tree and how it works. I will show a visualization of a radix tree via a visualizer soon enough, but like I said, won't be going into theory too much. So radix trees are a more compact version of a prefix tree or trie. In a trie, a node contains a single character. In a radix tree, a node can contain multiple characters which constitute a prefix. And because of this fact, you have fewer nodes and fewer pointers, which helps you in saving space, right? And all the leaf nodes in a radix tree represent a complete string, and I have this thing in brackets which says that leaves can exist at intermediate levels. It seems a bit counterintuitive if you think about your general tree like a binary tree or a binary search tree, where leaf nodes are only those nodes at the last levels of the tree. This might make a little more sense with the visualization, but yeah, just keep this in mind. And while a leaf node represents a complete string, it only stores the relevant prefix. So if I wanted to actually get the string that the leaf node represents, I have to combine all the prefixes on the path from the root to the leaf via concatenation, right? And then all operations against the tree are big O of k, where k is the key length. Right, so going to that visualization, I promised there is this radix tree visualizer. You can find it online. I will just insert some a key called rom, right? And you can see I get rom here, a node created with the string rom. I have an animation speed slider which I can adjust. I'll keep it somewhere here. Now another thing I want to point out, the difference between this and the implementation that I wish to touch upon, is that implementation has the concept of a root node which is more like a sentinel node, right? One that exists when you create the tree for the very first time, and which does not mean anything on its own, or rather it does not represent a string on its own. It's more to serve as a guide pointer. In this particular case, though, the root, when I did my first insert, the root is the string I attempted to insert itself. So that is one distinction. So just to bring up the root node, I'll insert the keyword Tom, right? And if you slow it down, you'll be able to read the stuff on the side. I suggest you do this on your own if you're interested. But you can see now I have this sort of root node, which is empty, which serves more like a guide. It does not represent a string on its own. And I have two leaf nodes, rom, tom, and I have edges with labels, right? These labels correspond to the first characters of the nodes I try to create. So I have r and t here. These edges will always be in lexicographic order, right? So now if I wanted to insert Romulus, right? So the thing is, Romulus shares a part of a prefix with Rom, right? So that it makes no sense in creating another node from root that points to Romulus. Again, to understand this, you can look at a Wikipedia page or some other resource to maybe understand the operations in detail. But what is going to happen is it is going to do some prefix matching. It is going to figure out that Romulus needs to be under Rom, and it is going to add this node, right? So you have an edge with label U now, and you have ULUS, the prefix, right? And like I said in one of the points on the slide, if you want to get what this node represents, you add all the prefixes on the path from the root to the leaf. So you had ROM and ULUS to get Romulus. This node represents Romulus. Now if I wanted to insert Rom, similar story. You can see, yeah, it does, and then it will insert E, and edges are still in lexicographic order. Now what if I wanted to delete Rom, right? ROM. Now also, before I actually do the delete operation, you can see that all these nodes are green, right? And you can think of all the green nodes as leaf nodes, right? And all the leaf nodes represent a string. So Rom is a string, Tom is a string, E is not a string on its own, but like I said, if you add the prefixes, you get Rom, and Rom is a string, and similarly Romulus is also a string in the tree, right? Hence, all of these leaf nodes, they represent a string, and that's why they're leaf nodes in the first place. And in the case of the visualizer, they are green. If I deleted Rom, you can see the green color disappears, and now Rom is no longer a leaf node because it does not represent a string. There is no string called Rom in the radix tree, but you can see that node is still kept around. The reason for that is because Rom is still a common prefix to its two child nodes, E and Ulus, which represent Rom and Romulus. What if I deleted Rom though, right? Now the moment Rom is gone, Rom is a common prefix only to Ulus, right? So Romulus is the only word beginning with R in this tree, right? So in this case, we do not need to keep the node that represents the common prefix around. So when you try to delete this, you will see what happens. I'll just speed up the animation, but yeah, you can see, right? You have Romulus and Tom because we didn't need that common prefix, so Rom around. But what if we wanted to insert Rom again? Now Rom shares a common prefix with Romulus, in which case node splitting will occur and your result would look something like this. I'll slow down the animation a little bit. I still don't think you can read stuff on the side, but yeah, it looks better, I guess. Nice animation. So yeah, this is what ends up happening. You have node splitting, and if I insert Rom again, you go back to what it was earlier. But yeah, I think this is a decent explanation of radix trees. You can experiment with it further. You also have find here. I did feel there are a few bugs with this. It didn't always work the way I want. Let's just see. Romulus. Yeah, it's a string not found. This is wrong, right? This is totally wrong. This is not the case. Romulus exists in the tree. I'm not sure if it's a bug or I'm pretty sure it's a bug actually. Yeah, node is string not found. Let me just refresh. If I had a single node around, what would happen? Yeah, if I search for Rom, it still says string not found. Okay, so if I wait, is it maybe the case? Yeah, string not found. That's weird, dude. That's really weird. Maybe I slow it down and read the text. I might understand why it's not working, but anyways, I don't care about this. Yeah, going on with the slides. Next slide. This is more about the specific implementation of radix trees. Immutable radix trees go this particular library, go-immutable-radix. Right? Immutability here means trees cannot be modified in place. Every modification returns a new tree. So the examples I showed via the visualizer, that is mutable radix tree, right? Inserts, deletes were all happening against the same tree, but not the case in this library. Immutability achieved via a mechanism called copy on write. Maybe some of the next slides that have some visuals will make that clearer. The thing about copy on write is it makes concurrent reads easier, and there is no need for read coordination. So you do not need mutexes. Okay. Save for use by a single writer. Multiple writers will require synchronization, meaning you again need mutexes, right? So this library is good for read heavy and low workloads. Okay, this library provides transaction support, and all modifies happen in the context of a transaction. Insert, deletes, updates to leaf values. Also, leaf nodes store key value pairs, right? This is another difference from the visualizer, and it is also a significant difference from some of the visuals I'll show you later. Some of the visuals later do not represent key value pairs, just keys. I kind of forgot about the value part when I made those visuals, but you can keep that in mind, right? Nodes are key value pairs, not keys. So the visualizer example, it was just keys, right? So okay, I deleted my tree, but anyways, going on. Modifications to a tree will require inserting, updating, deleting leaf nodes or intermediate nodes. This is straightforward. For any such modification, all nodes on the path from the root to the leaf along with relevant edges will be copied over. This is the actual copy on write part. Again, will be explained with visualizations soon enough. From the perspective of the code, any node that has been copied over is also modified if tracking mutations is enabled, and this library allows you to enable that feature to track mutations. Then the channels associated with these modified nodes or leaves will be used to signal mutation of the tree. Now this concept of channels, this concept of mutations, rather the concept of signaling and stuff, it is something Golang specific. It is a part of Go's concurrency model. So if you do not understand Go, then yeah, I don't think this particular thing would make sense even when I go through the code. But if you have an idea of Go, then I think you can understand what channels mean, right? So yeah, in the context of the code, modifying nodes is different from modifying leaves. I will touch upon this once again when I cover the code. Hopefully I remember it. And then leaves modified only, leaves are modified, I forgot the word are, leaves are modified only during delete or when we try to update the value associated with the leaf. When we try to update the value associated with the leaf, so say we have, just say we had rom in the rom, right? Say we had rom. No root node, but again I'll go on anyways, and say the value associated with rom was 10. Now, right now, what if I wanted to insert rom again, but with the value 20? In this case, what happens is no node needs to be inserted. It's just that the value 10 needs to be updated to 20. Again, it won't happen in place because we are immutable. It leads to a copy on write, but that's what I meant by updating value associated with the leaf, right? Therefore, leaves have their own channels for tracking leaf mutations, right? Because modifying nodes is not always modifying nodes and modifying leaves are usually different things, right? I mean, they're always different things in the context of the code. That is why leaves have their own channels for tracking mutations. Again, when I go through the code, it might make a bit more sense. But I will now go on to what copy on write, how it actually works, right, visually. So this is our original tree, something similar to what I might have showed you earlier. Rom is not a leaf node, it's not green because it does not represent a string, right? Rom represents a string, so E is green, Romulus is a string, so Ulysses is green. Now you want to insert Romulus is into a tree, right? If the tree was mutable, we could create a leaf node with prefix ES and attach it to node Ulysses via a new edge labeled E. However, this tree is immutable. I think this slide is fairly straightforward. So what actually happens, right? How is copy on write achieved visually? This slide, maybe let me turn it into a slideshow from now on. So yeah, the first thing we're going to do is create a leaf node ES. Actually, if you think about the insert operation of inserting Romuluses, it is going to start at the root node and we are going to recursively look for the point where we have to create the leaf node, right? Only after recursively finding that point will we create our leaf node. If you after we have created ES, like I mentioned, copy on write is copying over of all nodes on the path from root to the leaf along with their edges. So all the nodes include root node. In this case, they include the root node, they include rom, and they include Romulus, right? Because ES is supposed to I mean, it is meant to be under ULIS. That is why these are the relevant nodes that should be copied over, right? This node E, which represents Rome, it is not on the path, so it will not be copied over. So, like I said, copy over, we are going to copy over ULIS. Now, ULIS does not have an edge of its own. I'm talking about edges that are going out from ULIS. This edge that you can see that is attached to ULIS, it is actually edge originating from ROM, right? So that is not relevant at the moment. So we are copying over ULIS, but we also need to associate ULIS with our new leaf. So we create an edge with the label E. Similarly, we are going to copy over ROM, and we will be copying over the relevant edges. So we are copying over the edge to U, the edge to ULIS, and we will be copying over the edge to E. Right. So we can see that we have another edge to E as well now from the new ROM that is represented by dotted lines. In the context of the code itself, I mean, if you look at the code, it might be a little more complex. If I'm not wrong, it's not always as simple as copying over the edge. There is a little more that goes to at the code level. That should be obvious. But more on that later again. And our final step after this is to copy over the root node, and we have this, right? So the reason this would enable concurrency is because, say we have one Go routine or one thread that is currently maybe working with this tree, right? This original tree. And say we try to insert something, right? Maybe there is a writer, and we can have a single writer that is working concurrently with our readers, right? So it inserts something else. So while we are reading this tree, or while we are iterating, while we are processing it, this entire stuff can happen parallelly, right? Without the need for a mutex, without the need for any blocking, this entire process can happen. And now we can have another Go routine iterating through this tree as well, right? So again, we do not need any read coordination. And in the after creation of this tree, and after this tree was committed, if we insert another tree, we'll have another partial tree next to it. We'll have another series of copy and writes, and then we could have a Go routine reading that tree. All of this is possible without the need for blocking, right? This is what copy and write enables. If we were to modify the tree in place, we would need to use mutexes even for reads. So yeah, so copy and write is giving us this little performance boost because we are eliminating locking, but at the cost of extra space, right? Just to stress on this point, the reason we didn't copy over E is because it's not in the path. Technically, we could copy over all the nodes of a tree, and we do a copy and write. There is nothing stopping us. This is just an optimization, right? Since E is not on the path from the root to the leaf, it's not something that was that we need to create a new copy for, right? Because our new code, our new Go routine, it does not need a copy to E, because E, which represents Rome, is not involved in any way. We can just hold a pointer to this, right? If you want maybe more clarification, maybe if this explanation does not work for you, you can look at copy and write. I think there are other data structures you might find that use copy and write. For example, you can search for a copy and write B tree. I think there are some databases like LMDB or LevelDB, I think it is, and Bolt that use copy and write for B trees. That's also an interesting thing to look at. But yeah, previous slides involved a single insert. We could create a transaction and perform multiple inserts, deletes, and updates within the context of the transaction. If the current node has been modified during the course of a transaction, it is used in place for subsequent modifications. Copy and write won't happen again. Copy and write not necessary here, because until an actual commit happens, changes within a transaction not visible to the outside world. Yeah. So maybe some of this makes sense. We'll try. Let's see if the next slide helps. So reconsider the previous tree before adding Romulus's, right? This one. And now we are creating a transaction on our own, right? So we are starting a transaction, and we insert Romulus's, at which point all this entire process happens with copy and write. And we have two trees now, and we insert Romulus. Now we want to insert Romulus, right? Second step. You might think that we will have another series of copy and writes, and we create a third partial tree next to it. copying over the relevant edges and the relevant nodes and stuff. But as this previous slide explains, this particular tree that we have just created via copy and write is not yet visible to the outside world, right? The only reason you have copy and write is because you want to allow concurrent reads without read coordination, without mutexes. And read coordination is not relevant yet for this particular tree because this tree has not been committed, right? That is why you can choose to modify. It is preferred that you modify this tree in place. I mean, I'm not sure if you can say preferred. The code, that's what the code does, right? It is going to modify the tree in place. So when you try to insert Romulusans, it is going to create a new leaf ONS, but it is going to attach it to this particular existing ULUS, right? This ULUS was copied over during the last series of steps when you try to insert Romuluses, but it won't be copied over again, right? Now you're doing transaction end, right? I think that's it for the explanation. In subsequent video or videos, I will go over some fundamental pieces. Yeah, looking forward to that. Hope you understood something from the video. Hope there are some important takeaways. See you soon. Thanks.